I know that looks like Arrhenius, but trust me, it is not pronounced Arrhenius. Now, or Arrhenius, or anything like that. I'm pretty sure it is pronounced Arrhenius. That is the way that I have heard it pronounced before, and that sounds pretty good to me, so I'm going to go with Arrhenius. We're going to talk about the Arrhenius equation in this video today. This is an equation that relates K, the rate constant, and the energy of activation, or activation energy, whichever way you want to go. And it also relates it to the temperature. So this is essentially taking K, taking the rate constant, and kind of showing everything that's inside it, is really what this equation is doing. So the equation is shown here. So we have K is equal to A, which is what we call the frequency factor, and that is again related to how many molecules are making it into that transition state, or that activated complex per second, times E, and this is just the number E, the mathematical number E. So, the natural log is base E. This is the same thing here. So E raised to the negative energy of activation divided by R, and that is the gas constant, times T, the temperature in Kelvin. Okay, so we have all kinds of stuff in this equation. This is a very handy equation. It is very useful, but it is even more useful if we rearrange it just a little bit so that it is in a linear format. So this is the same equation we saw over here. We've just taken the natural log of both sides and then moved things around a little bit. So if you take a natural log of both sides, it gets rid of that E. And so now instead we have the natural log of K is equal to negative EA over R times 1 over T plus the natural log of the frequency factor A. And so we have y equals mx plus b. So our slope in this case is negative the energy of activation over the gas constant, as you can see here as well. The intercept is the natural log of the frequency factor, and then we have natural log of k and 1 over t as our variables. So if k is determined experimentally, we can actually use this equation and use the slope from doing multiple experiments to determine the energy of activation for the reaction that we are looking at, which is very, very useful. This is actually one of the easiest ways to determine the energy of activation for a reaction. It's just doing the reaction at multiple temperatures and using that to solve for EA in this equation. So let's do that. So we're not actually going to do the experiment. It was done for us here. But this is the decomposition of ozone. A study of the kinetics of the reaction shows this data. So they did a whole bunch of reactions here at very high temperatures. Even for Kelvin, normally Kelvin temperatures are pretty high. Room temperature in Kelvin is nearly 300. But these are even hotter. These are very, very hot. And so you can see the rate constants to go along with those. And this asks us to determine the value of the frequency factor, which is A, and the activation energy, which is EA. So we are going to go back to our trusty friend, Excel. So here we have the data input into Excel. And by the way, if you are inputting data in Excel and you're using scientific notation, you do not have to, like for this first one, for example here, that would be 3,370. You don't need to type that in, and you also don't need to do something like 3.37 times 10, raised to, like, you don't need to put in the math like that. What's much easier is just do 3.37 and then capital E and then 3. And so what that E is it is essentially standing in for scientific notation. So capital E is times 10 raised to whatever comes next. It is just like your graphing calculator, but you can do it in Excel. So instead of typing in times 10 raised to, or trying to actually get the correct number of zeros, you can just use a capital E for your engineering exponent is what that's called. All right, so anyway, we want to get A and EA using this data, and to do that, we need to make a plot of the natural log of k versus 1 over t. So if you remember, this was the equation. And I believe it is plus natural log of a. For some reason, I have a lot of trouble remembering if the last section here is plus or minus on multiple different equations, but I'm pretty sure that is plus natural log of a. You can go back and check me, make sure. But we're going to go ahead and move forward with it. So we need to figure out the natural log of the rate constant and 1 over the temperature. Now, the 1 over the temperature is going to be our x. Natural log of k is going to be our y. And so we want the 1 over the temperature to be the first column here. So just like in the previous video, I'm doing equal sign. 1 divided by that cell gives me 1 over the temperature. And then for my y values, I want the natural log of k. So I'm going to go here and say this cell is equal to ln, open parentheses, that cell, close parentheses, and then do the same for all the rest. And hopefully, this will give me a nice straight line. Looks pretty straight to me. So again, I'm going to right-click on a data point, add trend line, display the equation and the r-squared value, even though I don't really need the r-squared value. It's kind of nice to see it, though. So once again, we have a pre-prepared data, canned data as it is sometimes called, because we have a perfect r-squared value. Normal data is not perfect, but we'll go ahead and we'll work with it. So we are looking for two things here. We want A and we want EA. Sports, it's in the game. Ha 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 ha. Joke for the video. So some of you are really confused right now, and some of you thought, oh goodness, he just went there. Anyway, moving on. So if we're trying to find A, if you remember, the natural log of A is equal to the intercept. So we know the intercept. The intercept is 26.79. So if the natural log of A is equal to 26.79, hopefully you remember from your high school algebra how to remove the natural log here. That is to raise e to both sides. So if we raise e to the natural log of A and we raise e to 26.79, what we will end up with is A is equal to a really, really big number. Let me see. E raised to 26.79. Very large. 4.31, we'll say, times 10 to the 11. And I believe the units on that are per second, if I remember correctly. Since that is a frequency, it should have a unit of per second. So that would be the number of molecules per second that are reaching that transition state. So then the second thing we are looking for is the energy of activation, and that is equal to the slope. Well, actually, I should say, let me rephrase that. The slope is equal to the negative energy of activation divided by r. So it is related to the slope, but it is not equal to the slope. So our slope is negative 11,201. That is equal to negative EA over r. Those two negatives are going to cancel each other out, so I'm just going to ignore them from this point forward. And what I'm left with is just this number times r. So I'm going to multiply both sides by r to get rid of this over here. R, if you remember, we want the joules version of this. In Chem 1, we used a 0.08206, but that was liter atmospheres per mole K. We're dealing with energies now. We'd prefer not to use liter atmospheres. It's still technically correct, but it's a very cumbersome unit. Nobody really likes to use that, and so we're going to use joules instead. So 8.314 joules per mole K. I just remembered as 8 pi. So 8.314 joules per mole K. So we're going to multiply that by 11,201. And we will end up with the, not K, energy of activation is equal to 93,125.114. But we don't get to keep all those numbers, and it's usually, and this is going to be joules per mole. Are going to be the units on that. And usually this is written in kilojoules per mole, so we're going to go ahead and take sig figs into account and change it to kilojoules, and it will be 93.1 kilojoules per mole. All right. So hopefully that made sense. I do believe you have to do not necessarily this exact same thing, but something very, very similar in the homework. So feel free to come back and watch this again when you're working through that. And we're going to go ahead and call it there for this video. And the next one, we're going to look at the last big topic for the chapter, which is reaction mechanisms. So we'll start with that. We'll probably have to split that into 2 videos, but we'll see. But we'll start that up in the next one. So I'll see you there.